Hello again, everybody. Welcome to a new screencast lecture. I'm your host, Mr. Richards. Tonight's topic is absolute dating. Now, before you get too excited, this is about rocks. And let's take a look at the word absolute first. If you say the word absolute, what do you mean? What does that mean? What does the word absolute mean? Well, in this case, it means something that's perfect or certain. Or another way to look at it, which is probably more applicable to our topic tonight, is that it is viewed independently, not comparative to other things. For example, if you take a look at this, we have various people here. Here is a man. It says here he is from Mexico. Here's a man from Norway. You can see that the man from Mexico, compared to the man from Norway, the man from Mexico is shorter from Norway, who is taller than the man from Mexico. So when you compare two people, say this man is shorter than that man, you are doing what kind of height? Well, you are making a comparison, so it is relative height. If you take a look at the chart here, it says that this man is 5'7". That is his actual height, so that is his absolute height. And the man from Norway is 6 foot, and so that is his absolute height. And here are some famous actors. Some of these you may recognize. So here's this guy. It says here he is 7 foot tall. I have no idea who it is. It says his name is Vladimir something. And that goes all the way down here to 5 foot tall, which is Danny DeVito. And there may be some people here that you recognize as well. Like here's Johnny Depp. Woo.
He's 5 feet tall.
No, Johnny Depp is not 5 feet tall. I think it said he was 5. Let's see, let's go back. It says Johnny Depp is 6 foot tall. It's taller than I expected him to be, actually. So the people who are my height at 6'2" are Ryan Reynolds, Bill Murray, Hugh Jackman, and Jim Carrey. Here are some female actors. You see down here is Reese Witherspoon at 5'1", and I think this is Nicole Kidman, but I'm not really sure. According to this, she's 5'11". So those are her absolute heights. You would say that she is shorter than her. That is their relative heights. So absolute dating, let's talk about that. Absolute dating is the actual age of the rock or the object, and we normally measure that in years. Scientists are going to use the principle of radioactive decay in order to accurately date rock samples. So if you probably have heard that, like with a tree, you can see how many rings the tree has, and I'll give you how old the tree is in years. There is something called radioactive decay, which can help scientists to determine how old an object is by using this process. Now, before we go into this, we're going to give you a brief kind of rough idea of what radioactive decay is. This is not all-encompassing. If you want more information about this, you can ask me about it or do some research on your own. This is just going to be enough just so you have a basic idea of what's happening. So let's take a look at radioactive decay. So to start with, we must take a look at the nucleus of an atom, and this is something we learned in 6th grade. You may remember that atoms have a nucleus. You know that atoms have a nucleus, and in the nucleus there will be protons and neutrons. And outside the nucleus you're going to have electrons, but we're not worried about electrons with this. So an atom of helium, if you look at helium on the periodic table, helium has an atomic number of 2. That means it has 2 protons, and it has an atomic mass of 4, so we do 4 minus 2. That tells us that there are 2 neutrons. This is a normal atom of helium. This would be the most common isotope of helium. It has 4 total subatomic particles, 2 protons, 1, 2, plus 2 neutrons is 4. So this isotope is going to be called He4 or helium-4. Some atoms of helium may have different number of neutrons. Like, for example, this helium atom has 5 total protons plus neutrons. It has 2 protons still. It always has to have 2 protons, but in this case it has 3 neutrons. So this has helium-5 because it would be 1, 2 protons plus 3 neutrons. 1, 2, 3, 4, 5. Here is He6 or helium-6 because it has 2 protons plus 4 neutrons. 1, 2, 3, 4, 5, 6. I think you're starting to get the pattern here. So what would this isotope of helium be called? We'll take a look at this. What do you think, Y-Guy? What is the isotope of helium that we have here? Go ahead and count those protons and neutrons. Count, come on.
7.
7. All right, so this would be He7. Very good. All right. Well done. I'm impressed. Well, why are you counting by twos? It's okay. All right, so anyways, some isotopes are unstable and they break down into other isotopes and particles. So, for example, here is He7. He7 is an unstable isotope of helium, and helium-7 is going to decay. That's going to be the parent atom, and that parent atom is going to decay to the daughter isotope, He6. So what that means is it's going to lose a neutron. So He7 is going to decay to the daughter isotope, He6. Let's take a look. Here's a clip. Radioactive decay animation.
The nucleus of every atom is made up from protons and neutrons, about the same number of each. The nuclei of most atoms stay like this forever, but radioactive nuclei are unstable. They're like pieces of popcorn waiting to pop. Once in its life, a radioactive nucleus decays and throws out part of itself as radiation. Some atoms throw out a pair of protons and a pair of neutrons together as a particle. This is alpha radiation. Atoms of the same type always decay in the same way, so it's often possible to work out what type of atom is involved by detecting and measuring radiation. The radiation is a telltale clue to the atom which created it.
We're back. What are some isotopes that are unstable and experience radioactive decay? Well, there's a whole bunch. Uranium-238, carbon-14, that's the one we're really going to focus on tonight, and potassium-40. Those are three unstable atoms that decay that scientists and paleontologists really use for measuring the absolute ages for many, many different things. All right, now we know about atoms and a little bit about radioactive decay. Well, that's great. So what? So what do we do with this kind of things? Well, one of the things that's important to know is that different isotopes are going to decay at different and measurable rates. Like, for example, carbon-14 decays much faster than uranium-238. If you were to measure the amount of radioactive decay in a sample, you can measure the age of the fossil. Here's an example of how this works. Let's take a look at carbon-14 dating. Here's an atom of carbon-14, and the reason why it's carbon-14 is it has 1, 2, 3, 4, 5, 6, and then there's 6 protons, those are the red ones, and then 1, 2, 3, 4, 5, 6, 7, 8 neutrons. So 8 plus 6 is 14. The normal isotope for carbon would be carbon-12. This is a little bit unusual. This is an isotope of carbon. This is carbon-14. Let's take a look at our friend here. Here's a cow. And this cow is made out of carbon. As you know, we learned that before, that our living things are all carbon-based. We are carbon-based life forms. And some of the carbon in our bodies is carbon-14. Most of it's going to be carbon-12, but there is going to be some of the unstable carbon-14 in our bodies and in this cow's body. And here's our friend the cow. The cow has carbon-14 isotopes in its body. Most of the carbon in the cow is going to be normal carbon-12, but some of it is going to be carbon-14, and it is unstable and it will decay over time. However, our friend the cow is alive, and so it's going to be constantly eating, and as it eats, it's going to get some new carbon-14 from the grass that it eats. So it's always going to be constantly losing carbon-14, but it's also going to be constantly resupplying its carbon-14. So it loses some carbon-14, but then it eats grass, and then more carbon-14 gets put into the cow. Now, time goes by, and unfortunately, as time goes by, our cow ages and death kicks the bucket. Yes, that's a nice way to say it. So here's our friend the cow, no longer with us, unfortunately, and he does have 1, 2, 3, 4, 5, 6, 7, 8 atoms of carbon-14 in its body. It's going to have a lot more than that, but just for this case, we are going to do 8 of them. We're going to take a short time out. I wish I was sponsored by Diet Dr. Pepper, but I'm not. But it's good. If you work for Diet Dr. Pepper and you want to sponsor my show, please let me know. Drink it all the time, so I'll be happy to do that with my huge audience of almost 300 subscribers. We need, I think, 3 more subscribers. So come on, folks, if you're not subscribed yet, do so. I'd like to make that huge number 300. That would be a good Christmas present for me. Yes, thank you. So anyways, time goes by. Here's our friend Mr. Dead Cow now, and he gets buried underneath sediment. So now he's buried, and his bones are sitting there. And then over time, the carbon-14 is going to degrade and go away. And what you have here is that the half-life of carbon-14 is 5,730 years. For all practical purposes, let's just call it 6,000 years. So every 6,000 years is the half-life of carbon-14, yes?
Is that a lot?
That is a lot, yes. That's a lot of years. That's even older than me, believe it or not. And so, anyways, let's go take a look at the definition of what a half-life is, because you probably don't know. A half-life of an isotope is the time it takes for half of the atoms in the isotope to decay. Those are atoms. Those are carbon-14 isotopes. Those are carbon-14 atoms. Watch the screencast lecture, and then maybe you'll know. All right. We need. Shh. Thank you. I love you. Run along. All right, so the half-life of an isotope is the time that it takes for half of the atoms in the isotope to decay. So what that means is that for carbon-14, you have a half-life of about 6,000 years. So every 6,000 years, half of the number of isotopes that are in the cow are going to decay, and they are going to become nitrogen. So before the cow died, carbon-14 atoms were decaying and becoming nitrogen, but the cow, again, would continuously eat, so it would replenish that carbon-14 supply. But when the cow dies, of course, when the cow is dead, it's no longer eating anymore. So since it's not eating anymore, it's not getting any new carbon-14, and that carbon-14 supply is going to start degrading and start to become nitrogen. Over time, those carbon-14 atoms are going to decay and become nitrogen. After roughly 6,000 years, half of the remaining carbon-14 will have decayed. So we had 8, now we have 4. So 6,000 years have gone by. That is one half-life. So if we started with 8 grams of carbon-14, we now have 4 grams of carbon-14 remaining. After another 6,000 years, so now we're at a total of 12,000 years since the cow died, since the cow last ate and got new fresh carbon-14, there will be only 2 grams of carbon-14 remaining. One more half-life is going to be another 6,000 years, so now we're at 18,000 total years since our cow last had its final meal, and there will be 1 gram of carbon-14 remaining. And so just a little bit of carbon-14 remaining. So carbon-14 is good for organic matter. That means it had to be living at one time. It could be a tree, it could be a cow. It has to be something that was actually living, that would actually take in carbon. Also, it can't have been dead for much longer than 60,000 years. That's about the longest period of time that carbon-14 is considered to be accurate. This is not a complete explanation of carbon-14 dating. Again, if you want to learn more about it, ask me, look it up. There's a lot of good clips on YouTube that you can watch as well. We have as our scientist 18,000 years later. He's going to be digging around and he discovers this cow bone, and he's all excited. He wants to know how long ago the cow last had a meal, how long ago it died, and so he does a test to measure the amount of carbon-14 remaining in its skeleton, and he measures that it only has about 1/8 of the amount of carbon-14 that he expected it to have. So the living cow would have more carbon-14 than the cow bones would have. And it's about 12.5% in this case. So that is 3 half-lives, and we know that the half-life of carbon-14 is roughly 6,000 years, so you do 6,000 for 1 half-life, 12,000 for 2 half-lives, and then the third half-life tells me that it's been dead for 18,000 years. So our scientist now knows that our cow has been dead for 18,000 years.
Here's a clip.
Let's check it out. Here's a short clip.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this red water is the plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after 1 half-life, 24,000 years, diluting this water by half, it looks like this. After 2 half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear.
Well, that was a great clip, and now let's take a look at this chart. This is kind of neat. Carbon-14 dating, here's a chart that kind of shows us half-life and the amount of time that has gone by. So here's our tree that is still alive or just died. It has 100% of the expected amount of carbon-14 in it. The tree has been dead for 0 years. It has 100% of the expected carbon-14. After about 6,000 years, so 5,730 years, it only has 50% of the expected amount of carbon-14, so that's considered one half-life. After another 6,000 years, it's been dead for 11,460 years. It now has half of a half, which is 25% of the expected carbon-14. One more half-life, so it's half of a half of a half. Now we're at roughly 13%. It is of the amount of carbon-14 that you would expect it to have when it's living, and so that tells us it's been dead for 17,000 years. Here's the problem. What if you have something that, first of all, was not living? Because remember I said carbon-14 is only good for organic stuff. So you have something that was not living and or has been dead for much longer than 60,000 years. Well, if you have a case like that, you could look at other different isotopes like I mentioned. I mentioned uranium-238. Here, for example, you could use for potassium-40. If you take a look at the number of half-lives, so one half-life of potassium-40 is actually 1.3 billion years. So that's 1,300 million years. Okay, so that's a lot, and that's one half-life. You have something that looks like this. Now, notice this chart looks the same as the carbon-14 chart. It's just for a different amount of elapsed time. This line here shows you the amount of parent material, that is the potassium-40, and the potassium-40, when it decays to form argon. And so as the potassium decreases, the argon level will increase. That's what this is showing here. So after almost 8 billion years, almost all of the potassium-40 is gone and is degraded to form argon. Well, that's all we have for tonight, folks. Hope you enjoyed it. Hope you learned something. We'll catch you again next time. See ya.